In this video, I'm going to demonstrate a technique for solving a problem like the one stated at the top of the spreadsheet here, which is to find the x-coordinate of the point with the most negative slope for the function f of x equal x cubed minus 2x squared minus x. So what we're going to do here, I'm going to both plot the function just so we can see what's going on with it, and I will also use the values that I calculate. And to do both of these, what I need is a discrete set of values of x at which the function is to be evaluated, as well as the derivative. So I'm going to designate a column for the x values, a column for the function value at those x values, and a column for the derivative of the function at each of those x values. Instead of just writing the numbers at which I'm going to evaluate x here, I want to be a little bit more flexible. And so I'm going to set a changeable value of x naught over here, and let's say we'll just start with minus 5 to start with, and then a x final on the other end of 5. And we'll be able to change these, and the spreadsheet will automatically update. Now we need to decide how big a step to put between our x values. And so the way I'm going to do that, specifically for the sake of plotting, I'd like to have at least 100 points plotted so that the function comes out looking fairly smooth. So what I'll do here is I'll use the length of my interval. So the equal sign indicates the beginning of a formula. And the formula I want to use is the final value of the x interval minus the initial value. And then I divide that by 100. And so we're going to have to use 100 cells of the spreadsheet in order to go from minus 5 to 5 with this value of dx. So now I go over here, and I want to be able to change my bottom end, so I don't want to write minus 5 here. What I'm going to do is write a reference to it. So I write equal, and then highlight this one and enter that. So by doing that, what I'm doing here is I'm moving, as I start to type in the cell, I can move the arrows over and it automatically fills in the cell number that I'm on. So now I'm going to just hit return, and that gives me a mirror image of the entry in F4. Next, I want to add a small increment, my dx value, to that. So I want to use the predecessor cell, which is A4, and I'm going to add to that the value in F6. Now if I just typed F6, when I copy the formula over, it would shift down the page with the cell that I'm at. So what we do instead is we lock down both the column and the row as F6. And now when I copy this formula to the next cell, you can see that the A value went up to A5 because that is relative. Whenever you copy a formula, anything that doesn't have a dollar sign is always relative to the cell. So this one referred to the previous one, this one's going to refer to the previous one. But the F6 did not change, and that's because of the dollar signs. So now I'm going to copy this all the way down to 104. And there we see the expected 5 at the other end of the interval. So here I enter the formula for the function, which is given up here, so that is equal to, now the x value is the one in the box next to me, which is A4, and I'm going to cube that, subtract 2 times A4 squared, and then subtract A4. And that is the function x cubed minus 2x squared minus x. And that's the value of the function at minus 5. So now I can either hit Control-C or Apple-C, depending on what computer you use, and then highlight all of these cells and hit Control-V, or if your spreadsheet is clever, which Google Sheets is, and Excel, and most of the others that I'm familiar with, you can double-click on the bottom right corner and it automatically copies the formula you had in this cell to all of the ones that have a neighboring quantity all the way down to 104 here. So that is the value of the function. Now we have to figure out how to get the derivative of the function. To do that, we're not actually going to calculate the exact derivative, we're going to use a secant line approximation. So we'll take the slope of the secant line. And we can choose to either use the value of the function and the next cell or the value of the function in the previous cell. That would be using a negative value of h or a positive value of h. Since all our formulas always make it look like it's positive, I'll just do that. So we're going to use a slope of f of x plus h, the value of the function at the next point that I've evaluated at here, minus the value of the function at the current point, which is at x equals 5. And then I divide that by the value of the small interval that I'm using, which I'll use $f $6 to denote. And there it even highlights it for me. So now I can double click on this one, or Control C and Control V to all the boxes below, and I get all of my slopes. So now we could scroll down this list and find the slope with the steepest negative value, but let me first plot it just so we can see what we're looking at and get a better sense of it. So here I click on the little chart tool and choose, I want to use column A as labels, and I want a line graph. So here we get a line graph. That one looks great. And now it's automatically plotted both f and f prime. So we can change that by changing these intervals here. So if we go from A3 to C4, so if I want just the function, I can change that to B. Let's see, or I can go into select range. So I will get rid of this, and now I'm just gonna add another range, and that'll be sheet 1 B C3 to C104, and here I need it to be A104. So now it's going to skip the B column and only plot the derivative. You'll notice there's something funny going on here. So let's go see what that's about. Let's just insert that chart. Move it over so it's not quite as obstructive. And now we go down to that last cell and figure out what happened. So you'll notice this cell says minus 700, which is way out of whack. And that's because it's referring to a cell that I don't have any function value in. So let's just delete that one and omit it from the plot. And there we go, there's a nice quadratic, which is what we expect for the derivative. Now you can see that our minimum slope is going to be somewhere between 0 and 2. So let's update this. 0 and 2. And now it automatically updated our increment, it automatically updated all the slope values, and it replotted it. And now we can see that our lowest point is somewhere between 0.4 and 0.8. So we can go 0.4 and 0.8. And now we can further zoom in, further and further in on the function. Now eventually this is going to start looking very flat, and it'll be hard to determine from the graph where the minimum is. And so what we need to do in that case is we need to now scroll down through the numbers and just look for the steepest negative value, the largest negative value that we can find. So that's going to be somewhere around 0.67. So I can just page down until I get to 0.67, and we can see here that there's a 3332, 3333, 3332. So this looks like the lowest point, and it's going to be close to the lowest point, but that lowest point should be somewhere between the previous cell and the next cell. So we have a range through which we can be certain our minimum will lie. And that means we can only be certain of the 0.66, and this 4 is not necessarily so convincing. So we could go to a tighter and tighter interval up here and either refer to the graph or refer down to the minimum at the bottom. Either one will get us a better accuracy, but the graph may be difficult to see eventually. And that's how we find the minimum of f prime, or the steepest negative slope of f of x. Now there is another way to do this. We can add a column for f double prime and look for the 0 in that column. So let's actually do that just quickly. So I'm going to put f double prime here, and what formula do we want to use? Well, we could use exactly the same one that we used over here because we want the derivative of the neighboring column. And so if I copy that all the way down, now when I go to that 0.66 area over here, 0.66, this is what we thought was the min. And you can see that the slope goes from negative to positive right there. So we're really close to that minimum value. So as we change these values here, we should get better and better accuracy, both in finding the lowest value of f prime and the location of the zero of f double prime, which should coincide. And that gives you two different ways of identifying the minimum slope of f.